sorry, 0.22 times 85, and 722, this is reading it off the graph. The first two questions, I know the mic wasn't on, so that's just basic mole conversion. You can go over those. I'm not doing everything in here, but this stuff is under the Michael Farabaugh review for missing that. So then we would add it to the 87 times the 0.278. So you change the percentages to decimals, multiply them, and add them up, and we end up getting 85.56 AMUs or U. I think they use U in AP. What is the most likely identity of this element? Well, then you go to the periodic table and you look for 85 something or other. And my closest one is what? Rubidium. RB is the closest element that we're seeing here. So fill in the table below of two naturally occurring isotopes of this element. So the mass number, if it's 85, how many protons does rubidium have? Rubidium has 37, right? And the other one was 87. Still has only 37, so this one's easy. This one's 50 neutrons, and then 85 minus 37 gives me 48 neutrons for that one. Okay? So those are just the basic graphs of calculating average atomic mass. Just want to go back over that. So as you can see, periodic table found rubidium. As you can see, the answers are in there, so that's the closest. And then we would fill in these and get those answers. Okay? All right. I'm going to, for this one, what's the only thing that might seem maybe a little bit difficulty here? Gallium occurs naturally as a mixture of two stable isotopes. The information about one naturally occurring one is shown above. What is the average atomic mass? We would look at our periodic table. What's the average atomic mass for gallium? 69.72. Okay, now it says fill in the missing one up there. We can figure out what the mass number is of the other one because we should be able to figure out the percentage of the other one. Percentages should always add up to what? So the percentage of the other one should be what? So this should be 39. And then you would just work backwards in the equation to find the other isotope. Let's see what he did. Okay, 39x. Fill it in, like I said. And then you can figure out what the other isotope is. And it's probably going to be like 67 or 68. He does all the math for you. 70, I'm sorry, 71. 71. Okay. All right. Percent composition by mass of each element. Like I said, this is more Chem 1 stuff, so I'm not just going to be long. Find the average, or find the molar mass, and do each individual element over the molar mass to get your percentages. Those are pretty easy. Okay. This is definitely something like you learn in Chem 1. Certain compound has the following composition. Determine the empirical formula. This is the percent to mass, mass to mole, divide by small, multiply to whole idea. Okay, so we also do this a lot in Chem 1. But here, just to review the steps real quick, you assume a 100-gram sample because that's 100%. Okay, so then you take that one, change it to moles, carbon, then hydrogen to moles, then the sulfur to moles, and you look for the smallest mole. So the smallest moles is this top one here. That's the one we're going to divide by to get our ratio. And divide by, you get 1, you get 3, and you get 1.5. If you get a 0.5, you multiply by 2, which is the multiply till whole part. Okay? You got like a 0.33 or a 6.6, you multiply by 3. You get the idea. So multiply till whole, so that means 2 carbons, 6 hydrogens, and 3 sulfurs. So that would be your empirical formula. Remember empirical formula? Still the basics here of Chem 1 stuff. Okay. Like I said, this is all under the Michael Farabaugh folder there, and you can pull down the PowerPoints at any time too if you want to go back and refresh anything. All right, so determine the mass of the carbon. This is combustion analysis. I'm going to kind of skip through this. Once again, we do this in Chem 1, but you can go back over the combustion analysis on your own. He does it both ways like I do. He teaches it both ways like I do, so yay. Okay. And then you have to do the, find the empirical formula. This one has the 3, 3, and the 6, 7 one, so remember you would multiply by 3 there, as you can see, to get your organic compound. All right, mixture here. Mixture of CaCl2 and CaSO4. It contains 28.25% by mass here. All right, so calculate the percentage of the CaCl2 in this mass here. Basically here, assume the total mass is 100 grams again, and the mass of the Cl present is 28.25, okay? Find the molar mass of your individual compounds here, okay? And then you can use that to figure out the ratio there of your chlorine to your calcium chloride. So in the calcium chloride total there, 70.9 of it is the chlorine. So you're using kind of a reverse way of dimensional analysis here. Okay? So that's going to give you the amount that is from the calcium chloride of the 100 grams. So the percent by mass of the mixture times 100, 44.22. All right, mixture has a mass of 13.5 grams and contains this amount of sodium nitrate and this amount of sodium carbonate. So you basically have to figure out the percentage of the sodium. So you need to figure out how much of the 5.25 grams is actually from sodium and how much of the 8.25 grams are from the sodium to be able to figure out it out of the entire mixture. So you would do that individually for each compound. Okay, 2 components in the mixture. Okay, so molar mass of the sodium nitrate here. Once again, the molar mass of those. You don't have to spend time doing that, but we're going to take our 5.25 here of the grams of the sodium nitrate. It won't make you calculate molar mass, but we're going to use the molar mass and the sodium and work it to sodium alone. Okay, so in the 85 grams, 22.99 of that formula happens to come from the sodium. Okay, so of the 5.25, one there, 1.42 grams of that 5.25 is from the sodium's mass and not from the nitrate's mass. Okay, but you have to do the same thing for the other compound in there, the 8.25 of the sodium carbonate. So in here, basically the total mass is 105.99, but here, because there's 2 sodiums, don't forget that you would have to do 22.99 times 2 for the top number. That's where we get that top number, is because there's 2 of them in the compound. Okay? and you figure out of the 8.25, that 3.579 happened to be from the sodium there. You need to add those two together with the total amount of the sodium, and then you're going to divide it by the mass of the mixture to get its percentage in the mixture. Okay, add those together, then set them over the mass of the mixture, and you get your percentage there. Now, I don't know why he's going out so many decimal places. I would have kept these to 3. This would be 1.42 for me and 3.58. Those would be for me. And then this would have been, I guess this would have ended up being 5.00 for me. So I would have made this 5.00, and then I would only go out 3 here, so 37.0% probably is what it would be. I don't know why it's going out so many sig figs there, but the measured values are the ones in the problem, so the two components, the sodium nitrate and the sodium carbonate, those ones only have 3, I would go with 3. Okay, electron configuration. Gotta remember how to do our ions here. Okay? Ground state electron configurations. So that means you're pretty much starting at the top of the table and working through it. Strontium, if you're looking at my periodic table, is going to land on 5s2 right here. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6. Now remember that 4s comes before 3d, right? 4s2, 3d10, 4p6. And then 5s2 is where strontium, ground state strontium, would end in that particular column. Now, ion-wise, where do you always remove electrons from if we're doing a cation? Always from the most outer energy level, which should be the S or the P from that energy level first. So, which one would get removed here for the strontium? We would remove the 5s. So basically, you would have this whole thing right here up until 4p6. Okay? The two that are in the 5s would get removed to form the ion. Now, for the zinc goes down to 3d10. Okay, so zinc ends on 3d10. Now, if we're going to remove 2 electrons to do the zinc ion, which one's going to be removed? This one's going to be removed, so you would rewrite it without the 4s. S and P's go first, then you start removing from the same energy level if it has a D, if you have to remove more. Okay? So make sure that you do that. You remove from the higher energy levels. Okay? So as you can see, he's loading it down. Oh, look, it's very nice in this periodic table. And then down there to 5s2. So that would be 5s2. Very good. Then, oh, he's saying you can do the noble gas configuration if you wanted to. But if we're removing it, okay, ions, when electrons are removed from an atom, cation, they're always removed from the first occupied orbital's largest principal number. That's why he said the S and P's usually go first. Okay. Now here, to go to zinc, 3d10, as you can see that. Okay. Once again, for removing it, you're going to remove it from the 4s, right there, and get your final configuration. PES diagram, photoelectron spectroscopy. Write the correct symbol for the element. Which side do I start? Which side is closest to the nucleus where I would start the 1s? The higher numbers or the lower numbers? Higher numbers. So this side over here, that's your 1s. This is 2s, 2p, 3s, 3p, and 4s. And how high does it go? 2. It goes up to 4s2. So if I'm looking at 4s2, that element happens to be what? Ca, calcium. Very good. So this is calcium. Okay, 1s, 2s. As you can see, that's the configuration. And that's going to be calcium. You got it right. Very good. Okay. Partial photoelectron spectroscopy of fluorine is shown above. On the spectrum above, draw the missing peak that corresponds to the electrons in the 2p. Okay? So, draw the missing peak that corresponds to the electrons in the 2p. So, 1s2, 2s2. Where would I put the 2p? To the right of the peak over here on this side, or do I put it over here on this side? Which one is the 1s, by the way? Left one. This one has to be the 1s because it has the larger number. So that means this is the 2s. So where is my peak go? Next to this, and I go up how many? 5. Very good. 1, 2, 3, 4, 3, 4, 5. So my peak would be like right here, like so. Because fluorine lands on 2p5, so that's its last electron that fills. But it would have to be a little bit to the right of the 2s because it's a little bit higher in energy. So see, lovely, 2p5 like we did, right there, right next to it. Very good. Which element, S or Cl, has a smaller value for its atomic radius? Justify your answer in terms of atomic structure and Coulomb's law. Oh, fun. S or and Cl, are they in the same row or the same group? Same row, so as we talked about, that's going to be based off of what?
Proton.
Proton number, they have the same number of principal energy levels, so their R value of the Coulomb's law on the bottom is going to be virtually the same. But because chlorine has 17 protons, sulfur has 16 protons, it's going to have a little bit more magnitude of charge on the top of the Coulomb's law equation, higher effective nuclear charge. Okay, so here is our Coulomb's law. And remember, this number is going to be virtually the same because they both have n equals 3 energy levels, and they both go out to the 3p for their last energy level. But because chlorine has one more proton than sulfur on the top number, that's going to make its force, its coulombic force, the force with the coulomb there, it's going to make that slightly higher. And therefore, because it's stronger, it's going to pull in those outer electrons in just a little bit and make the radius smaller. Okay? So, like so. So I would say because, chlorine up here, chlorine has 17 protons, S has 16 protons. This number right here on the top is going to be larger for the chlorine. Okay, and therefore it is going to be stronger force of attraction pulling the cloud. Okay, like so, right next to each other. Valence electrons are located in the same energy level, so you would need to note that, like I said, same energy level, n equals 3. That's important. Okay, and then you would compare the proton numbers, has a greater nuclear charge with one more proton. Oops. So Cl has more protons than S, and I would specifically state, chlorine has 17, sulfur has 16. Has a smaller value for its atomic radius because the electrons are more strongly attracted towards the nucleus. Okay? Oh, this looks like fun. Ionization energy defined as the energy required to remove 1 mole of electrons from 1 mole of gaseous or atoms or ions in their ground states. Removing outermost electron from a neutral atom is called the first ionization energy. Which element, S or sulfur or selenium, has greater value for its first ionization energy? Justify your answer in terms of atomic structure. Coulomb's law. Now, this one has to do with them being in a what? Same column. So now same column, if we're talking about Coulomb's law, we're talking about the denominator, the R squared value, the distance. Okay? So here, looking at them, comparing them, S has 3 principal energy levels, whereas selenium has 4 principal energy levels, both going out to the p orbitals, like so. Valence electrons are located in different energy levels, n equals 3 and n equals 4. So the n equals 4 has a greater distance. Greater distance is going to weaken the force of the attraction. Okay? So when comparing atoms of different elements located in the same group, valence electrons are located in different energy levels. Electrons located in higher energy level are farther away. Keyword distance. Farther away. Electrons located in lower energy level are closer. So according to Coulomb's law, smaller distance between oppositely charged particles, the greater the attractive force. Okay, so we are going for, here we're talking about has the greater value for the first ionization energy, so we would say n equals 3, the shorter distance for sulfur. Okay. Closer to the nucleus, so has a greater value for the first ionization energy. You can cite Coulomb's law. You can do the F is proportional to Q1, Q2 over R squared, and then talk about the R squared value being the effective one, messing with the force of attraction there. Okay? But down the group, talk about the energy level, be specific with the energy level, talk about that it's a farther distance, and that weakens the force of the attraction. You can note Coulomb's law in that particular deal as well. Or you could talk like this, about the farther distance means weaker force of the attraction, means you need to input less energy to overcome the force holding the electron and be able to remove it. So you do need to know your definitions of your trends like radius, size of the cloud, ionization energy, energy to remove an electron. The other major one, electronegativity, attraction for electrons in a chemical bond, things like that. All right, electronegativity, arrange the following elements in order of increasing electronegativity. What do we know about that trend? Where is the most electronegative element on the table? Fluorine. So up and to the right, carbon, nitrogen, and silicon here. So out of those, which one's going to have the highest? Nitrogen out of these 3 would be the largest, so I'd put N over here. And out of, which one would be the lowest? Which is in between? In between would be carbon, silicon would be the lowest. Very good. Silicon is down a row, so it has 1 more energy level. So that's going to bring more distance, so it's going to weaken the force of the attraction. Nitrogen has 1 more proton than carbon, so it's going to be a little bit stronger, and it's going to be a little bit more attractive for the electrons in a chemical bond. So as you can see, they're kind of right next to each other. Okay? Increase, increase, decrease. Yes, okay, so we got those right. Successive ionization energies. This is a good one. Do you remember successive ionization energies? No, not really. Okay, so we're going to go over these. What are we looking for here? We're looking for the significant jump in energy. So when they give you successive ionization energies, I can identify it's between the 3rd and the 4th one there. You see it? Successive ionization energy jumps. What does that tell us about our particular element here, element X? What group is it in?
Yeah, no, I think, because I do think the percent error is really just that high.
If it has, this means this is the end of the valence electrons. Whatever element X is, it has 3 valence electrons. So what group is it from?
It doesn't matter. Absolutely not.
Group 13 or 3A? Group 13 or 3A, right? Okay. So that's important to be able to identify the group based off of the valence electron number. So how many does it have? It has 3. Why? Because there is a significant jump in ionization energy between the 3rd and 4th. That means the 3rd electron is the last of the valence, and that the 4th electron is called a what? A core electron. And core electrons take a lot more energy to remove than valence electrons. So very good. Is all coming back to you now? Okay, valence electrons. I like, oh, he shades it. That's so cool. Okay. Core electrons. Okay, element X has 3 valence electrons because there's a big increase. When the 4th is removed, this is because the inner shell core electrons are much closer to the nucleus, require more energy to remove. All right. Write the empirical formula that should be formed between element X and oxygen then. What should be the normal charge on element X then? If it's in group 13 or 3A. 3 plus. So we would say X is going to be 3 plus. What is O going to be? 2 minus. So this is going to be X2O3. For our chemical formula, right? That's how it would be. So, as you can see, the charges up here. We're looking for that one and that one, and combine them together. We got ours. Okay, so element X has 3, carries a 3 plus. Oxygen has 6, so it's minus 2. And remember, you need to get the right ratio to make them add up to 0. So that's why you would need 2 of the plus 3's of X, 3 of the minus 2's of O, so that it adds up to equaling 0. Yes?
So, like, on the left side, it's all, like, positive, and on the right side, it's all negative, but in that graph you just showed us.
Oh, we can go back, yes. So here. So the 4th column is plus or minus 4, but most of the elements in the 4th column don't form ions. They just do covalent bonding. So a lot of times people will leave it off, but when I teach this during Chem 1, I do plus or minus 4. Because technically, yes, there are some, occasional ions in there, but for the most part, carbon, silicon, those ones are going to do covalent bonding. They don't really form ions. Yeah. Well, those are all first ionizations, but that's just a regular trend. Remember, first ionization is up and to the right. So to remove the first electron follows that trend. There's a few exceptions to first ionization energy. That's usually between what group 2 and 3 or 2 and 13, and then or is it 2 and 13 and 15 and 16? Yes, those are the exceptions for ionization energy. But I don't know if they'll actually ask those. When you're talking first ionization energy, you're only talking about removing the first one. But if they give you successive ones, that's like taking off the first one, then the second one, then the third one. So it's removing it from the same atom. Okay? Sure. Okay. All right, a certain element has located in period 2 of the periodic table and has the same number of valence electrons as X. Write the symbol O. Period 2, can we figure out what that one is? That's going to be what? That's going to be boron. Boron is in period 2. So that is going to be our element there. Very good. Very, very good. All right. So I believe we're at the end there of summative part 1. Or summative for unit 1. Like I said, though, you can go back through these, and there's the individual topic notes and also in there under the Michael Farabaugh review if you'd like to look at those.